Hello everyone. Today we will solve this second numerical example, which is you can see is taken from the exam paper of 2007. So in this case, as you can see that you are given a textile machine which run at a speed of 250 revolution per minute. So the given data is the omega, which is the mean angular velocity, is 250 rpm, revolution per minute, and you are given the three identical units which are powered from a common drive shaft by a single electric motor. And figure, which is this figure here, it shows the simplified torque diagram for a single unit of the machine, and the unit are phased at 120 or 2 pi by 3 radians to each other. So this diagram is given for a single unit, but you will have to combine three similar diagrams. So the part A here is that you have to calculate the determine the mean torque required to drive the machine. So you have to calculate the mean torque here. So to calculate the mean torque, first we need to construct the torque diagram, the overall torque diagram for the whole machine, which consists of three such a contribution, but are phased at 120 degrees, which is 2 pi by 3 radians. So to draw the diagram, what we can do is that if you draw these diagrams here. So this is the okay, so on the x-axis we have the crank angle, which is increasing in this direction here, and this is in radians. And on the y-axis we have torque, which is in the Newton meter here. Okay, so the first thing is that you need to draw the torque diagram here. So the one that is given is that 0 is here, and you have this 2500, which is this point here, and then you have this 7500, which is this point here. So this is our 0, this is 2500, and this is 7500 here. So what you can do is that you just draw horizontal lines here. Okay, so if for the first cylinder, we will just repeat this plot here. So as you can see, it's 2500 from 0 to pi. So the angles here are 0, and then it's pi by 3, 2 pi by 3, and 3 pi by 3, which is pi here, and then 4 pi by 3, and 5 pi by 3, and finally it's 6 pi by 3, which is 2 pi here. So in this case, what we can do now is that we just need to draw the torque diagram for the first system here. So it's going 0 from 0 to pi, and then from pi to pi by 3 it's going then to 7500. So it's going there, and then after 60 and 60, so after 120 degrees it's going to 0, So this is for the first system here. Now if you want to draw the similar diagram for the next unit, so it will be 60-degree out of phase. So so this one, as you can see, is starting here. So the next one should start at 60 degrees, at 120 degrees. So this is 60 and this is 120, so you should start it from here, and again then it should go to this point here, which is 7500, and then it should goes to 0 here. So in the two blocks, so it will goes to 0 here, and then again it's 0 here, and again it is 0 0 here. And now for the third unit, so as you can see, this starting at this point here and going here, and then after two blocks, which is 120 degrees, it's starting from here. So the next one should start from one block, and then second block, so it should start from here. And if we want to draw this in a different color, so you can draw it here. So it will goes to 75 here, and then then this part that you want to draw for it, so it should goes then to here. So it should goes to this point here. So this is now the and it's then 0 from here, 2500 from here to here. So this is the torque diagram for the three units, and obviously this is the input to a textile machine. So this is the input torque, this is not the output torque. Okay, so in this case, as you can see, this is the overall torque diagram for the three units. Now we need to draw the overall a single torque diagram for these from these three diagrams, which you can even do in the same figure here. So in the same figure, if you just expand this a little bit here, okay, so as you can see, at the starting point it is 2500. So for the two units it is 2500, and then for the one unit it is 7500. So this means that at this point the torque is 7500 plus 2500 and plus 2500. So 7500 plus 5000, which is 12,500. So the value should go to this point here, which is 12,500, and the units is obviously Newton meter, and then this point here is between the two lines here. So this point here is 5,000. So if you just draw another line here, so this one is 5,000 here. So if you look at this this line here, so at this line you have two torques, which is 2500, and one torque which is 5,000. So 5,000 plus 5,000, which will become 10,000. So this means that we should have a point here which should be 10,000 here. So you can draw another line of 10,000 here. So, and then similar idea can be applied to the other points. So again, at this point you have two plots, which is 2500, and one is 7500 here. So again it will become 12,500, which is this point here. And then at this next location, which is at pi, so you have two plots, which is 2500, and one is 5,000. So the results will be 10,000 here. So this will be the point, and the next, then this point, and then this point, and then you have this point here. So now if you just join these points, so if you join these points, so this is the overall torque diagram, which is the red color here, and the other three you can just point that out, that the red color is the torque diagram for unit 1. The green one you can say is unit 2, and then this one was for unit 3, and the red one that you see here is the overall torque diagram. Which is simply unit 1, the torque diagram for unit 1 plus unit 2 and plus unit 3. So when you add the contribution of all the 3 units, so you should get this overall torque diagram, which is changing from 10,000 to 12,500. As you can see here, this is the overall torque diagram, the one with the red color here. So now the part A of the question is that what you need to calculate is determine the mean torque required to drive the machine. So in this case, you need to calculate the mean torque here, which we will calculate from this. So part A is that you need to calculate T mean, which you should calculate from this plot here. So again, you can use the similar idea that you should calculate, for example, all the areas here. So you can calculate this areas, and then you can so the equation for the T means is that you calculate the net area, and then you divide it by the base length. So in this case, as you can see, you have 3 triangles, which is 2 this one, and then this one will make 1 triangle. So you can calculate the area of these 3 triangles, and then you divide by the 2 pi, so you will get the mean torque. But in this case, because it's relatively straightforward, because these are just equal triangles, and again you can see that the positive area and this negative areas, which is here, are exactly the same. So what you can do is that if you want to calculate the mean torque in this specific case, so you can just find out the average of these 2 torques, which is 12,500 plus 10,000, and divided by 2. So this will give you a value which is 11,250 Newton meter. So this is the mean torque in this case. In the part B, now what we need to calculate is that during initial testing of the machine, a trial flywheel with a moment of inertia of 30 kg/m² was fitted directly to the motor drive shaft, and the speed fluctuation was found to be plus minus 1%. Determine the combined moment of inertia of the electric motor and drive shaft. Okay, so in part B, what you need to find out in the part B is that the system, if you want to draw the system here, so you have the electric motor here, which is, you can say this is our motor, and then you have the flywheel, which is attached directly to the to this drive shaft of the motor. So this is our flywheel, And then here you have the our machine here, the textile machine. And in this specific case, in the part B, you are given that the I of the flywheel is 30 kilogram meter square. Obviously, you are also given the omega in the previous case, which was 250 rpm, which is this value here. And now again, what is given here is that the was found to be plus minus 1%. So the speed fluctuation is also given. Which is plus minus 1%. From this, you can calculate the omega 1 minus omega 2 divided by omega, which is the fractional speed fluctuation. So now the requirement is that determine the combined moment of inertia of the electric motor and drive shaft. So what we need to calculate is the I of the electric motor and drive shaft. So this I is unknown in this specific case. Now we know that that we can use this equation here, that delta E, which is the maximum energy fluctuation, is equal to I, and in this case, because we have a system which consists of a motor, a drive shaft which is between the motor and the machine, and then you have a flywheel. So all these parts have their own inertia. The inertia which is given for the flywheel is 30 kilogram meter square, but the inertia for the motor and the drive shaft is not given. So we can say that this is the total moment of inertia, and this I total is the moment of inertia of the flywheel plus the moment of inertia of the electric motor and drive shaft. So in this case, we need to calculate the this IEM ds, which is the moment of inertia of the electric motor and drive shaft. So if we calculate this I total, from the I total, because we know the I for the flywheel, so we can calculate this I for the electric motor and drive shaft. So we will use our usual equation for the maximum energy fluctuation. So I total and omega square, and then you have omega 1 minus omega 2 divided by omega. Okay, so this equation now we need to calculate is that you are given the value of the omega, and you are also given the value of the fractional speed fluctuation, which is omega 1 minus omega 2 divided by omega. So divided by omega, which you can calculate from this value here, and we did this in the previous examples, that you will just this will become 0.02, which was explained in a quite detail in the worked example 1. So if you are not clear how we get this value, please go and look back example 1 in the previous lecture. Okay, so if we know this value, if we know the moment of inertia, and we know the omega square, now we need to calculate this delta E maximum, which we can calculate from the combined or from the overall torque diagram. So if you want to draw the overall torque diagram again here, so this was how it was looked like. So it was 10,000 here, and then this was 12,500 here, and you can split this into different angles here, and this was our crank angle, and this is our torque, and this is zero angle. This is pi by 3, 2 pi by 3, and this is pi. 4 pi by 3, 5 pi by 3, and this is 2 pi. So in this case, the torque diagram was that, so it was going to this point here, and then it was going to this point here, and then this point. So this is how the torque diagram looked like for this specific case. And we also managed to calculate the mean torque, which was in between the 2 points, and the mean torque was 11,250. So 11,250 was this point here. So now you can shade the positive and negative areas here. So as you can see, this is the positive area here, and again this is the positive area which is above the mean torque. So we are shading this with the red color here, and then you have the area which is below the mean torque. So which is we will shade this as a blue color here. So in this specific example, as you can see, that the that you have 10,000 here, and 12,500 here, and 11,250 here. Now you need to calculate delta E maximum. So delta E maximum is the energy which changes the angular velocity from minimum to maximum, or from maximum to minimum. So in this case, if you see, so this area here, this is the delta E maximum, because this will change the speed from the maximum to minimum, and again this will change the speed from minimum to maximum. This will change the speed from maximum to minimum, and so on. So in this figure, all these areas, so for example this area is delta E maximum. Similarly, this area is delta E maximum, and if you add these two areas together, so these are also delta E maximum. So if you call this A1 and call this A2, so if you add A1 and A2, so this will become delta E maximum. Similarly, these area, so this is again delta E maximum, and similarly this area is delta E maximum, and similarly this area is delta E maximum. So in this case, it's then straightforward to calculate delta E maximum, which is going to be the area of any of these triangles which are exactly the same. So if you take this triangle here, so for this triangle, if you want to draw this triangle, so the base of this triangle is you can see that it's going from pi by 3 to pi. So the base of this triangle is half of this, and then half of this section here. So it's pi by 3 from here to here. So this means that it is pi by 6 is from here to here. So this is pi by 6, and this is also pi by 6. So the total length from this point to this point, which is from this point to this point, is pi by 3. And now to calculate the height, so the height in this case is 12,500 minus 11,250, which is 1250 here. So the height here is 1250. Then it is straightforward to calculate this area, which is delta E maximum. So in this case, it's going to be half pi by 3 and 1250. So from here then you can calculate the area of this triangle, which will become 1250 pi by 6. So just if you want to keep it like this. Okay, so now you can put the values in the equation, in this equation here. So if you put the values here, we should get the value of the I total here. So to put delta E maximum, which is 1250 pi by 6, on the right hand side we have I total, and then you have omega square, which is given is 250, but obviously you will need to multiply this with 2 pi divided by 60 to change this to radian per second. And then you have this omega 1 minus omega 2 divided by omega, so which is, we know that it is 0.02. So from this equation, the only unknown is this moment of inertia for the total system, and this will become 47.75, and the unit will be kilogram meter square. So now as you can see here, that I total is equal to I flywheel plus I of the electric motor and drive shaft. So now you can calculate the I of the flywheel. So what you can calculate here is that I of the flywheel plus I of the electric motor and drive shaft is equal to 47.75, but we know the value for the I of the flywheel, which is 30. So if you subtract 30 from here, you should get this value here, so which again the unit will be kilogram meter square. Okay, so now in part C, we will try to calculate. So this is the part C that is given here. So now you have in a revised design, it was decided to replace the drive flywheel with a new one, designed to run at 3 times the speed of the drive shaft, and sized to control the speed fluctuation to plus minus 0.5%. So now you need to determine the moment of inertia of this replaced flywheel. Okay, so now you have a new design in this case, and the new design is going to be that you have this motor here. This is part C. Okay, and the motor is now connected to the flywheel using some sort of gears here. So the flywheel is connected here, and so this is our flywheel, and this is the unit, the textile machine. So now in this revised design, the speed of the flywheel, so the omega of the flywheel is 3 times the omega for the drive shaft, which was given in the previous case was 250. Okay, so now we have this new system, and you're also given that that you have to control the speed fluctuation to plus minus 0.5%. So speed fluctuation is now given, which is plus minus 0.5%. So if the speed fluctuation is given is plus minus 0.5%, so we can calculate the fractional speed fluctuation, which is omega 1 minus omega 2 divided by omega, and this will become 0.01. So you just multiply this with 2 and then divide it by 100, so you will get the fractional speed fluctuation. So now in this case, what you need to calculate is the moment of inertia of the flywheel now. So the unknown is the moment of inertia of the flywheel. Now obviously we can use our usual equation for the maximum energy fluctuation, which is this equation here. So delta E, which is maximum, is equal to I omega, and then you have omega 1 minus omega 2 divided by omega. Now in this case you will need to modify this equation slightly, because the here now we have two systems. One is flywheel, and one is the electric motor and drive shaft. So we will split the right hand side into two parts. So we can say that this is for the whole system. So now we need to split this into two parts. So the equation we will modify is delta E maximum. So I of the flywheel, omega of the flywheel, and this omega 1 minus omega 2 divided by omega is constant for both. And then you will have plus, and then you have I for the which is given is this value here. So I for the electric motor and drive shaft, and then you have omega. Again you can say it's for electric motor and drive shaft, and then you have omega 1 minus omega 2 divided by omega. Okay, so now this is the final equation. Now in this case, delta E maximum is again you can take it from this value here, which was which you calculated here or here, because the units are the same, so there will be no change in this delta E maximum. So you can just use this previous value here, which is 1250 pi divided by 6. So 1250 and pi divided by 6. On the right hand side you have I of the flywheel, which is unknown, and now omega of the flywheel, which is this value here. So this is 3 times the 250, which is the angular velocity for the previous case. So it was 250 there. So you will, and this is omega square. Okay, so 3 times 250 and into 2 pi divided by 60. You need to convert this into radian per second, and square is here, and then the fractional speed fluctuation is 0.01, and then again the moment of inertia for the electric motor and drive shaft. So you calculated it in the previous part, in the part B, which is 17.75. So you can just take that value 17.75, and then omega is again 250. So 250, and again convert it into radian per second, and then square, and then you will just multiply with 0.01. Now in this equation the only unknown is I for the flywheel. So you can calculate I for the flywheel here, and that will become equal to 8.64 kilogram meter square. Now as you can see, the size of the flywheel is reduced in this case, and the reason is because the flywheel is now rotating at higher speed, 3 times the speed of the previous case. In the previous case, the flywheel was connected directly to the drive shaft, so which was here, but now it's connected to the using some gearing system, and it's connected like in this figure here. and in this case the flywheel speed is 3 times the speed of the drive shaft. So that's why the requirement of the size of the flywheel reduced. So it's reduced by so you can see the previous case it was 30 and now it's reduced to 8.64. Now we need to solve the part D here. So in the part D, it's saying that during maintenance work, the machine is operated with one of the unit disconnected. So you disconnect one of the unit here. So construct the torque diagram for this arrangement and comment on the effect on speed fluctuation. So what you're going to do here is that in the part D, you are disconnecting one of the units. So then in the previous cases, so A, B, C, there were 3 units in the previous cases, but now it will become only 2 units. So we will need to construct the torque diagram again for only 2 system here. So if you, for example, consider only 2 units here, so okay, so if you consider this this system here, and this is obviously crank angle, and on the y-axis we have torque, which is increasing in this direction here. The crank angle is increasing in this direction here, and the angles here are 0, pi by 3, 2 pi by 3, 3 pi by 3, which is pi, and then you have 4 pi by 3, 5 pi by 3, and then 6 pi by 3, which is 2 pi here. Okay, so in this case, what do you have here is that if you consider this is again the same torque diagram, so 2500, and then you have 7500 here. So the way the diagram is changing is for the first unit here. So it was constant from 0 to 2 pi, and then it's going to this value here, and then it's going to 2 pi here. This was unit 1, and now we can consider only one other unit because now we have only 2 units here. So in this case, assume that you are considering this unit here. So this one here, and then you will have the then it will be 0, it will be 2500 from here onward. So this is our unit 1, and now this is our unit 2, and there is no unit 3. So now from these 2 units we now need to construct the overall torque diagram. So the overall torque diagram in this case will be, we should now again need to draw it here, for example. Okay, so in this case, as you can see that at this point here, what do you have here is that the you have a value of 2500. So one is 2500, and then you have 7500. So in the previous case there were 2 2500, but now we have only one 2500. So if you add 2500 and 7500, you will get 10,000 here. So you will get 10,000. So you get 1 point, which is this point here. And now here then you get 2500 and 2500, because there are two units here. So the next point that you will get is this point here. So you get this 10,000, and this is 5,000 here. And then obviously there is no change from 2 pi by 3 to pi, so this will remain the same. So it will be again 5,000 at angle pi, but again at 4 pi by 3, which is this point here. So again you have 7500 and 2500, so which will again be equal to 10,000. So again you get 10,000 here. So here you get 10,000, and then at this point here, so again okay, so now at 5 pi by 3, you want to calculate the value here. So at this point you have one is 2500, and we know that this value here this is 5,000 here. So this value is between these 2 points, the 5,000, and at this 5 pi by 3 you have 2500, and then you have 5,000, so it will become 7,500. So this value will become 7,500. And finally at the end point, which is 2 pi, again you have two values, one is 2500 and one is 7,500. So you will get 10,000 here. So if you join these points, so what you can get, you will get this line here, then it's 5,000 here, it's going to 10,000, and then it's coming back to 7500, and then again it's going to 10,000 here. So this is now the overall torque diagram. So we can say that now this is the overall. And obviously on the x-axis we have here this is 0, this is pi by 3, this is 2 pi by 3, this is pi, this is 4 pi by 3, and this is 5 pi by 3, and this is 2 pi here. Okay, now in this case because now we need to find out the if you read the description of point D, so you need to calculate the speed fluctuation here. So to calculate the speed fluctuation, obviously you will need to use the same equation, that delta E maximum equal to I omega square, omega 1 minus omega 2 divided by omega. So again we are using the same equation here. So to use this equation, obviously you need to now calculate delta E maximum, and delta E maximum we can calculate from this plot here, from this new plot. And if you look at this new plot, in this new plot what do you have is that you will need to calculate the mean torque here. So to calculate first the mean torque, the one way is to calculate the net area, and then you divide it by the base length. So using this equation you will need to calculate this area of the triangle here, and then you will need to calculate, but you will need to do this from zero torque line. But in this case, you can use a simple trick, and the trick will be, because in the if you go to the previous case here, so in this case, this was the first case here, and in the first case the mean torque was 11,250, and this torque was for 3 units. But in our case now we have only 2 units now. So what we can do is that we can just multiply this this value by 2 by 3. So we will get the new mean torque. So you don't even need to do the calculations. So what I will suggest, that to save time, we will not even use this equation here, but how we will calculate the mean torque here, that we will take the previous torque, the previous mean torque, which was for the 3 units, and which was 11,250, and you will multiply this with 2 by 3. So this means that now we have only 2 units out of 3 units. So if you calculate this value, you will get 7,500 Newton meter. And if you do not believe in this equation, so you will just need to calculate all the areas, and then try to use this equation, and you should get the same answer here. But this is just the simple trick. Okay, so now we have this the mean torque, which is 7500 here. So now to calculate delta E maximum, we will now draw this mean torque line here, and now we can shade the areas which are above the mean line and below the mean line. So below the mean line we will shade is a blue as usual, which is this area here, and area above the mean line we will shade is red color, as you can see here. So the blue is the negative area, and the red are our positive areas. And again we can see that if we take this, this is our point A, this is point B, this is point C, and this you can call it point D, and point E here. Okay, so now in this case, what do you have is that you have now mainly 2 areas. So one is the positive areas, and then you have a negative area. Now to calculate delta E maximum, it's very straightforward to look at this this figure here. So what you can see, because all these positive areas are attached to each other, so what will happen, that these positive areas will change the speed of the crankshaft from minimum to maximum, and then this blue area will change the speed of the crankshaft from maximum to minimum. So this means that the delta E in this case is either these 3 areas. So if you sum all these 3 areas, you should get delta E maximum. In another word, you can calculate this blue area, and again it should give you the same value of the delta E maximum. And because this 7500 is the mean line, so this means that the red areas which are above the mean line is exactly the same as the area which is below the mean line. So let's try to calculate this blue area here. So if you say this is delta E maximum, so we can calculate delta E maximum. Now in this case, as you can see that this consists of this rectangle, and you have 2 triangles. So one is this triangle is a little bit longer, and this is a shorter triangle. So we can calculate these 3 areas now. So if you look at the rectangle here, so the rectangle is just pi by 3. So because this is pi by 3, so this is pi by 3 from here to here, and the height of this rectangle is from 5000 to 7500. which is 2500. So into 2500, and then for this triangle here, you can see that again the base of the triangle is pi by 3 and the height is of the triangle is 2500. So you can calculate its area, which is half times pi by 3 times 2500. So this is area of this triangle here. Now for this triangle, because we know that this is the midpoint here, so this distance is obviously equal to pi by 6. So now the height is 2500, the base is pi by 6, so the angle, the area will become half into pi by 6 into 2500. So if you do all this calculation here, what you will get for this delta E maximum, you should get 7 by 6 into 1250 pi. So you will get this value here. Now if you consider the previous value of the delta E maximum, which was 1250 pi divided by 6, so this was the value for the 3 units, and this new value here is for 2 units. So now what you need to do now, you need to talk about the speed fluctuation now. So again, if you can consider the same equation, that delta E maximum equal to I omega square omega 1 minus omega 2 divided by omega, so which is obviously this equation here. So because now we have this equation here, if you split this into the flywheel and into the electric motor and drive shaft, so in this equation either you put all the values and then you calculate omega 1 minus omega 2 divided by omega, and from which then you can calculate the speed fluctuation, or you can use a simple trick that because there is no change on the right hand side, the only change now is on the left hand side in the energy, and the inner energy fluctuation, the new energy fluctuation is 7 times the old one, so which is 7 by 6 into 1250 pi, and in the new and in the old case it was just 1 by 6. So this means that the new energy, so if you call this the delta E maximum for 2 units, this is equal to the 7 times the delta E maximum for the 3 units. So you even don't need to do any calculation, you can just simply say that what will happen to the speed fluctuation so the new speed fluctuation will be 7 times the old speed fluctuation, which is plus minus 0.5, and if you do this calculation, so you will get plus minus 3.5%. If you don't believe these calculation here, you just use the previous equation and put all the values, and you should get the same value here. But this is obviously a simple trick to save time, and especially for your exam. So thank you very much.